Hey guys, this is Danica,
And this is Jordan.
and we are going to be going through our presentation 1, discussing different types of simulations for Engineering 460 today. So first, before we jump in, we wanted to discuss what is simulation. Simulation is simply creating a copy of a real-world process or system and then making sure that it accurately replicates or models that real-world process. In the education realm, we often use software like Simio or MATLAB to do these simulations, and a reoccurring problem that we do for simulation would be like patients coming in and out of an ER. The 3 different types of simulation that we're going to discuss today is discrete, continuous, and Monte Carlo. Let's jump right into the discrete event simulation. Discrete event simulation is the process of having discrete events recorded. So it's not continuous, they are individual, independent events that are occurring. And when the event takes place, the state of the system is changing from the previous event and the time recorded. So a good example of this would be following an individual going through a queuing system. A good example would be like if they were going to the DMV. So we all know when we go to the DMV, it takes forever. And part of that is because there's so many steps to it. So if I walk into the DMV, first I have to wait in line to even go talk to the first cashier lady. And she goes, "What are you doing here today?" And I tell her, and she gives me a number. And then I have to wait again. And then I'm going to go up to one counter. And then maybe I go to another counter. So in that example, there's multiple discrete events happening. There's waiting, there's talking to one cashier, there's more waiting, talking to a different cashier, and nothing is happening in the system between each of those events, which allows the system to run quickly for our discrete event simulation. But your system has different events, which is different than states. So the state is like the state of waiting, the state of talking to the cashier, whereas the event is like the end of that state and moving on to the next state. We're going to really briefly go through the key components of discrete. Those are state, the clock, the event schedule, the random number generator, the performance metrics, and the ending condition. So a state, as I kind of previously stated, it's the step function almost in which all of the things are happening in the discrete event simulation. So there's very specific start and end points to a state. And then when the state changes, that's what we call an event, and no values are recorded during a state. You're not recording like how many times people are talking or anything like that. However, one of the things we do record is that there's a clock keeping track of how much time is passing during each of those states. And like when an event occurs, that would be kind of when we would like hit the timer and say, okay, they're moving on to the next state. An event schedule, I also feel like you could kind of almost call this a flow chart. You are moving from one, like through the system. So things have to happen in a certain order. However, there's a difference between single-threaded and multi-threaded, which Jordan will discuss.
So a single-threaded event, discrete event system will have one event happening after another. There can only be one event that is taking place at a certain time. A multi-threaded event schedule is when more events than one can happen at one time. Typically, when you have a multi-threaded event a discrete event schedule, you have to keep track of when exactly the ending condition of the system is. Moving on, we're going to be moving to a random number generator. Typically, we needed to know how long a state will last. How long does a person at the DMV line have to wait before they go talk to the next person at the desk? So we're using a random number generator, typically Poisson distribution for stuff like DMV, how many people are coming in, that type of thing, and then using some other distributions. This is typically just to figure out how long somebody stays in a certain state. Moving on, we're going to performance metrics. Whenever you are timing all these things and you have an event, you aren't just determining how long it is. You need to determine how many people are in the system at a certain time. You need to determine how long that specific person has been in there. So this is basically just are we all recording all the right things at an event in a discrete event system? Moving on. Our last thing in a discrete event simulation is the ending condition. When do we say that it has ended? Is it when all of the customers has gone through the DMV in a certain day? Is it after a certain number of hours that the DMV is open? Typically, it's stuff like that.
Moving on to the next type of simulation, continuous simulation. This is different than discrete simulation because it is continuous. There aren't multiple states that are happening. You just are continually recording in the system. So here, technically you could say that it is discrete event simulation, but with infinite states. But because it's difficult to measure those infinite states continuously, we can do it, but you would need to use a lot of calculus and other math. The next part of this are the key components. So we'll go over the performance metrics, the behavior, and ODEs, ordinary differential equations. So for performance metrics, this is very similar to when we were talking about discrete. You have to be measuring something as the simulation is occurring. So how many people are in the system, etc. The example that we give for continuous is almost like if a cannonball was shot. So if you continuously shot cannonballs out of a system, you could simulate like the normal track that a cannonball would take if you had the cannon at a certain angle. But there's other little factors that go into that, like the wind and, just how the cannonball was like not perfectly symmetrical or whatever. So if we simulate the cannonball being shot over and over, that's a continuous system because the cannonball doesn't go through like one state after another. It's just continuously being shot. And during that continuously being shot, we would be recording different metrics.
Okay, so moving on from there, let's take on the cannonball example. So the cannonball typically takes a certain flight pattern or a typical path. We know this equation. It's learned in Physics 1. Typically, it's just related to gravity. But let's say that we don't know that. We could take a lot of data, and we could take at a certain time the cannonball was this high from the ground, and we could take multiple pieces of data like that and use it to figure out what the behavior of the cannonball is. The model typically has a behavior tending towards certain values. Continuous simulation often like models this physical, like when the cannonball is flying through the air. And typically, whenever you have all these data points, you have to use differential equations to model it. Differential equations usually just has a ax plus by typical way of thinking about it, but it's figuring out those constants in front of it that will figure out what the model is. So moving on to that, we're going to get to differential equations, ODEs. Typically, these are the ways that people typically model physical realm, typically model things that are continuous. And typically when you use the ODEs, you have to have multiple, you have to have a set of ODEs, as they say, to really model complex systems. This can actually get kind of hard. Differential equations is tough in itself, but to model continuous real world things is actually relatively difficult. This typically involves a lot of high level math, and typically it is kind of strenuous and doesn't always give you pretty answers.
This all brings us to the last simulation type, which is Monte Carlo. This is actually the type of simulation that our class is based on. Monte Carlo is essentially what you use when you can't use anything else. It's used when these mathematical approaches are very difficult or impossible even to solve. So the strength of Monte Carlo is that it's extremely versatile. Another thing about Monte Carlo is that it is often used for risk analysis, or when we don't really know the distribution of things. So jumping into the history really quick before we talk about the key components is Jordan.
Okay, so before Monte Carlo, typically they would use a distribution to measure uncertainties, and they'd take data and they would relay it to a distribution and try to find uncertainties. But as we find out with Monte Carlo, they actually flipped it and using probability distributions to figure out data and to figure out things to plug into a certain equation. A lot of early Monte Carlo has relation to Markov chains. That was how the first problem ever did with Monte Carlo was really ever done. It was by Stanislaw Ulam with the Los Alamos project. He was part of the Manhattan Project, which was trying to formulate nuclear weapons in World War II. On a medical leave in, I think, Italy, he basically figured out by using a game of solitaire. Basically, he was trying to figure out if you had a certain set of cards, how likely would you be to success. So basically, with the power of computers, he basically tried to figure out what's the probability with a certain set of cards that you're going to get a success and you're going to win the game. And he applied this to the nuclear bomb by saying when you shoot a neutron into a uranium atom, how likely will it be to hit the right atoms at the right time and bounce off so that it will have the explosion. This is how it is related to Markov chains, because what is the probability once it hits one, it hits another one, and then hits another one. So that's why Markov chains and Monte Carlo have been really, really combined from the start. So moving on, we're going to be talking about the key components in the Monte Carlo, which is domain, probability distributions, deterministic algorithm, and aggregating the results.
So the domain in Monte Carlo, before you set up your problem, you have to figure out under what domain are we speaking about. So a lot of times we talk about the total area under a curve, and you need to decide is this from 0 to infinity, negative infinity to infinity, from 0 to 5, etc. You have to set up the domain. And then the piece that is so difficult sometimes to Monte Carlo is you need to figure out what probability distribution does your data currently look most like. So some of the probability distributions that we use often are uniform, exponential, Poisson, normal distribution. So we use those to try and figure out what we're going to use in Monte Carlo moving forward.
So after we have sampled from the distribution, we need to determine deterministic algorithm. So basically this is how do we divvy up the samples to being a success, fail, within a certain range, within a certain area, approaching a certain number, that typical thing. Typically we would either plug this into an equation or we would relay it as an inequality greater than a certain value. After we do that, then we have to aggregate the results. What we mean by aggregate the results is once we have categorized all the data from the sample, we need to come up with the ratios, the means, the stuff like that. This would be the final relaying the final data of successes versus failures, that type of way. Okay, so now we're going to get into an example of pi. This will be really quick. Let's say you don't have the formula for pi, the area formula, and you don't know how to really do it. They originally did it with radius and circumference, but let's say we don't have those methods. We would figure out the total area of a unicircle, since it's very easy to do that. We would randomly distribute based on a uniform series, and we would plot whether the area is inside or outside of the circle, and take it as a ratio of the total area. That ratio would approach the value of pi.
Our last slide here is just the difference between these simulations, just kind of as a refresher. So the discrete event simulations are fast, but they rely on there being those very distinct events happening. And then the continuous simulation could be described as an infinite discrete event simulation, but this is often slower and it's often used to model physical phenomenon. And then Monte Carlo can model both of these distributions, but it relies on the user selecting the right probability distribution, and it's often used for risk analysis. So hope this was helpful. Thanks for watching.